So good afternoon and welcome to Parallel Sysplex Performance Topics. And now you're here, I can begin. I wonder how many of you actually get the reference to our podcast, because that's one of the ways we tend to begin. So, over recent years, RMF's Parallel Sysplex instrumentation has come on in leaps and bounds, right? And really the point of this presentation is to take you through some of the many ways you can use that instrumentation to drive lines of inquiry that you might have never thought you could, or maybe never thought you wanted to. So hopefully it will be enlightening. So for example, a while back, coupling facility CPU data model was enhanced to give much more granularity. Okay? And one of my favorite topics, coupling facility links, the instrumentation for those is very much enhanced. Okay. So this is really a from the field view of using this stuff to drive lines of inquiry with many customers, some of whom may indeed be in this room. I really can't remember. But I can't keep track of who works for who nowadays, so no hope there. So we'll talk about structure level CPU, as I mentioned, and then I'm going to talk a bit more about the matchup between the partition data report view of CPU for coupling facilities and their internal view, which is the 70 subtype 1 and 74 subtype 4 views respectively. We'll talk about structure duplexing and a little bit about async coupling facility duplexing as the new big thing. We'll talk a little bit about some uses of XCF traffic information. We'll talk about link information, as I say, tiny bit on thin interrupts, and a few bits and pieces on the new Z14 machine, the enhancements that come with that. We probably won't get to a detailed discussion on this little item, which is why I've shoved it in the appendix. Okay, it's quite readable, the slides, which I borrowed from Mark Brooks. So probably we'll leave that for when you get seriously bored one day. Okay, and some conclusions in the middle of that. Okay, so let's take the first topic, which is structure level CPU. So the field that is of interest to me is, and there'll be a test at the end, R744 set M, which is, as the name suggests, from 74 subtype 4 structure execution time, meaning CPU used in the coupling facility in support of that particular structure. Okay. Now, one of the key things to note, unusually, is when you add up all the values for R744 set M, you end up with the headline utilization of the coupling facility from the point of view of the CFCC code that runs there. Okay. There are lots of nice uses of this instrumentation. So the obvious one, and possibly the one it was intended for, is to do capacity planning for changing request rates. So if you expect to double the number of requests per second to a group buffer pool, maybe the CPU driven by that will double, and you can actually do proper capacity planning that way. You might equally, this should be equally familiar to you as an idea, want to work out which are the big consumers, because maybe you want to stomp on them. Computing the CPU cost of a request is kind of a handy thing to do, as we will see, particularly because you then compare it to service time to understand things like link protocol time. So the interesting number, as I say, is the non-CPU component of service time, as we shall see in a couple of examples. So, for example, we can work out from this set of data how things have degraded if they had. And we can estimate structure duplexing costs. So if you're going to take a structure like a lot 1 and duplex it, obviously the CPU is going to be replicated in the other coupling facility. Well, how big is it? At least you will know. One of the key things here, and this reinforces something I say about all RMF data, is in this particular case, you absolutely do need to collect the 74 subtype 4 data from all the ZOS systems sharing to get total request rate. Because otherwise, CPU per request is going to have too small a divisor because you're missing the traffic from certain systems, maybe uncertain ones. Okay, so that plays with a theme of mine, which is get RMF data, whatever you're doing with it, from all the systems you possibly can in the Plex and machines to get a complete picture.
Can you differentiate between normal list sort of CPU and the sort of cast out stroke and validation CPU, because that's single threads? So
not yet.
That can pause your access to the
Right.
facility.
Right, so the question was, can we distinguish between cast out CPU and the normal requests? Not at present. Now, the reason why I'm hesitating in answering that is because there's some new instrumentation which was late breaking after I put this together, which talks about the size of requests in support of coupling facility encryption, right? Which is possibly where that question came from. Now, what I don't yet know, and I don't think the CPU numbers will support it, is whether you can do anything useful with that, except for if you have data points with lots of cast outs and data points without, maybe you can do some kind of compare, but not inherent in the data, as far as I know.
Yeah, so I ended up with pauses of buffer pool, of actual access to the structure, because we had such large cast outs. I had to add another engine to the coupling facility so it doesn't single thread anymore.
Right.
And I have no way of instrumenting that, so what is this pause and how long is it actually really taking?
Right, all you know is the structure CPU.
It's single threads on the cast out bit. No one else.
Right, right. So adding engines might not. Yeah. Okay. Right. Well, I might have a nice surprise for you now I think about it, because there was a use of some instrumentation we'll talk about in a minute that might help you a little bit on that, but not fully, to be honest. Okay. So here is the obvious headline usage. So this is a coupling facility, and I've broken down the CPU in the coupling facility as a percent of an engine. I almost always work with percent of engines, sometimes percent of pool, but that's not relevant here. By individual structures, now there are 7 here, and you can see this one called CQST message queue is probably the biggest, and then this lock 1 for this data sharing group called DB2 DS0E. Probably DS0E is the name of the data sharing group. And there are some other structures, much less weighty. So the point is, if you're going to, let's say, double the lock 1's CPU, then this is the thing that's doubling and nothing else. So it's standard capacity planning, I would say. So that's just a basic use of the data, probably what it was intended for. Although, as I always like to say, nobody says what SMF is for. It's up to you to figure it out, right? Because you can find some creative uses. So I'm going to take you through some data-driven examples of things you can do with this structure-level instrumentation. So I piggybacked on a project in the ITSO in Poughkeepsie that was doing some stuff with parallel sysplex performance, and took the data. And now you have to bear in mind, in this little set of data, number one, we have 1-minute RMF intervals, which is unusual, but I don't think materially changes the numbers in a useful way. And secondly, all the requests to these structures were synchronous. And one of the things I'm doing these days, more and more, is graphing not by time of day, but with load. So here we have request rate increasing, which will be on the x-axis of some graphs I'll share with you in a minute. The run was essentially one-way DB2 data sharing, so the only really active structures were one called ISG lock and one which is a lock 1. In what follows, the red lines on the graphs are the CPU time per request, and as you'll see, it's important to get the request rate right to be able to get the CPU time per request right in this story. The blue lines are service time, or maybe, if you like, response time per request, of an average request. So the ISG lock case is low volume, meaning not high request rates. Compare and contrast the lock 1 case, which is higher volume. I wouldn't say high volume nowadays. So I'm going to just skip a couple of bullet points here and come back to them. So this coupling facility, well, these are 2 coupling facilities. The ISG lock 1 is in one using internal coupling links, right? So the simulated links. This one, the lock 1 case, is using a mixture of ISC and ICB links, which are quite old links now, but the age of them really doesn't matter for the telling of this particular story. So let's take ISG lock first, which is the low request rate case. So the red number here, CPU time, is basically descending from quite a high number per request as the request rate builds up to quite a low one, but it's leveling off. The point about that is because there's a 100% capture ratio, this here probably is fixed cost no matter how few requests you do. So this has a 1 over something kind of curve shape to it, right? The service time is basically more or less the same as the CPU time as these two converge because of the amortization effect dying away. So this is the case with IC links, so there are no physical links, they're just internal coupling links, where the time difference between the CPU and the service time is small or negative, right? By the way, I'm quite comfortable that the red line here, which is CPU time, is just above the blue one. Not because that's structurally meaningful, but that's just typical of the noisiness of the data. Okay? So this is a low use case showing off more amortization, basically is what it does. And oh, by the way, we get down to about 3 microseconds of CPU in the coupling facility per request here. So that's probably quite a good capacity planning number. Pro rata up with the higher request rate, and you will see probably 3 mics per request as a reasonable number to be using for capacity planning. Low use case, that one. High use case is the lock 1 structure. Now remember, this is over real physical links with some real distance to them. We will come back to distance later on in the presentation. So the CPU down here is possibly gently sloping down, possibly constant per request. By the way, just to repeat, this is the request rates. And notice it's quite a narrow range of request rates here, it turns out. So we don't really have the amortization effect anymore. That's going to be way off over to the left on the graph, if there were data points for it. The interesting thing here, to my mind, is the difference between the service time. Notice there's a bit of untidiness just here, but never mind. Live with it. And the CPU time. So this is going to be to do with link protocol time, latency. As I say, we will come back to that one. Again, you can probably take this number. Maybe you want the 3.5 mics per request. This is another lock structure, by the way. As your pro rata of the cost of doing a request. Okay. Again, you can see why it's important to have the right divisor in terms of request rates. So from all the systems, in this case there is only one, so it's easy. So that's a higher volume case. I don't think I need to go back because I think I've said all that. So from my travels, I ran into another interesting case. I keep running into interesting cases actually. This is from a real customer system in the middle of a crit sit, which really wasn't about this particular topic that I'm about to share with you. Okay. This is an old case, so the numbers themselves are old. So this is actually not a lock structure anymore. This is a group buffer pool, so a cache structure, and it's not duplexed. It's ISC connected, and it's ISC connected because the distances between the coupling facility machine and the coupled machines are long enough to actually require ISC connection. So that's, if you like, long reach style of link, but an old one. So let me do this and see if I can cover the ground. So again, the request rates along the x-axis. Up the y-axis is the service time or the CPU time. So we're doing fine, I would say, a bit of up and down, but we're doing fine until we hit about 1,100 requests a second. And then all hell breaks loose. By the way, there is a bit of an uptick in CPU here, possibly because all hell breaks loose. Bit hard to nail that one down, and it might be back to what you were saying about mixtures of requests. Maybe we're doing a hell of a lot of cast outs now, and those are quite expensive. Who knows? The point here is there's a compelling reason to go fix this if you ever want to go past this point, and guess what? You do, because you clearly are already. So just to recap a little bit on that. Something goes wrong about 11,000 requests a second. especially in response time, but also CPU. Okay. By the way, the coupling facility itself was not CPU constrained, I have to hasten to add. So there are some options here, and this is the real reason for coming back one slide. So, can you manage the request rate down to below 1100 a second? Right. Well, maybe you can for a while. Maybe you can't. This is sort of DB2 difficult data sharing stuff, right? And I butt out at that point, maybe. Can you work on the request mix? Back to the question we had just now. More likely, though, in the long run, you're going to want to think about infrastructure in the hardware sense. So maybe there is something about the configuration that needs fixing. Maybe it's more paths, maybe it's faster engines, maybe it's moving the machines closer together, who knows? But those are the sorts of categories of resolution, and all that kind of hangs on what happens with rate, not what happens by time of day. Now, of course, you could work out what those times of day were. That's still there in the data, right? It's time-stamped. So you could understand what the story is as to what sort of work is going on here. Maybe it's batch or something. Who knows? So that's quite a nice real-world example. So staying on the CPU theme a little bit, one of the things that's worth thinking about is how to match up the 70 subtype 1 partition data view of CPU for a coupling facility and the 74 subtype 4 view, which is the coupling facility's own view of CPU. So the first thing to remember is, from the 70 subtype 1 perspective, coupling facility engines, ICFs, if you run them in the coupling facility engine pool, that's pool 5, a separate pool, and you should always report on separate processor pools individually. Sizing-wise, of course, there are special coupling facility sizing guidelines, especially for the with considerations like white space, so for when you have to take over when you lose a coupling facility. They always run at full speed. If you're talking about ICF engines, they always run at full speed. So that's actually automatically a good technology match for coupled engines on the same footprint. It's never going to be too fast. It's not going to be too slow. And of course, as we saw before, you get very nice numbers out of IC links. The prevailing advice is not to use shared ICFs for production. The one thing I would say, which might be a little controversial, is thin interrupts, which we'll come back to in a minute, which is part of the reason for putting this slide up in the first place, or this section anyway. I'm not convinced they solve the problem of sharing coupling facility engines, for the simple reason when you want it, somebody else has got it. And that stays the rule with thin interrupts. Slightly better, somewhat better in fact. Okay. And obviously, unlike general purpose engines, you don't run them to 100%, which is stating the obvious, I should imagine. And as I say, especially if we need to be able to recover structures into a coupling facility. Now, I'd assume all that is utterly familiar stuff. So one thing to bear in mind is the 74 subtype 4 view is different from the partition data report 70 subtype 1 view. And we have a pair of fields at the engine level, which might actually help a little bit in the case we were talking about earlier. So we have a field called pBusy, which is the CPU time spent processing requests or looking for work, I think I should probably add. Actually, that's wrong. It is just processing requests. The pwait time is the time when the coupling facility engine is dispatched but not processing requests. So that really is where it's looking for work. Okay. Now, one thing to bear in mind is the whole point of thin interrupts is going to be to reduce that pwait time, which means you will be able to release the engine, because the pwait time is holding the engine, be able to release the engine to other sharers of the physical engine pool sooner. Okay. One of the points I think I would make, and I've yet to find a great use for this, is you can examine the individual engine P busy and P wait times in the coupling facility from 74 subtype 4 data down at the individual engine level if you so choose, because you might find there's skew there, which is back to the point that you just made some time ago. Okay. One of the difficulties we used to have before this quite old APAR was trying to work out which physical engine on the machine, which logical engines corresponded with which coupling facility engines. And the point here is we now have coupling facility LPAR partition number, which allows us to do the match directly. Okay. By the way, this APAR, which is an OMF APAR, was introduced to support ZHPF high performance FICON, and also introduced all the stuff we know and love about hyper dispatch, high, medium, and low characterized processes. So this is the thing that makes the match possible between the partition data view and the coupling facility activity view. So we'll come back to that a little bit in a minute as the story unfolds. So let's talk about structure duplexing for a moment or two. So what does it do? Basically, what we're talking about here is having two copies of the structure, one in each coupling facility. By the way, you may well have more than two. So when I say one in each, I'm simplifying a little bit. And depending on whether we're talking about system-managed duplexing or user-managed duplexing, some, well, all or some, as I've got it that way around, of the requests happen in both places. So for system-managed duplexing, the requests happen in both places. The cost is taken in both places. There is communication between the two coupling facilities to sync up, and that takes time. For user-managed duplexing, it's only the updates that are done in the secondary copy of the coupling facility structure. All the updates happen to the primary. Okay. So that all takes additional physical resources. So the second coupling facility, in this case, the secondary one, is actually documented as being the secondary in the 74 subtype 4 record that refers to the primary. So you can always find out which coupling facilities are documented together. Okay, you're going to tell me I know my estate. Actually, those of you who I count as long-standing friends in the room will know it's a pain in the neck to document your estate and keep track of it, right? Particularly as things are getting more complex. So it's really nice that all this stuff is self-documenting for you if you ask the right questions of the data. But, you know, so maybe this is not the best example of that, because you probably do know what the secondary coupling facility is for your primary. By the way, I don't, unless I've worked with your data before, and it's possibly changed since I did. Okay, so second coupling facility, more CPU in that second coupling facility, possibly a tiny bit more CPU in the coupled ZOS systems, additional memory, obviously, but actually the white space rules say that isn't necessarily so. White space rules basically say we've got to be able to recover the coupling facility structure in another coupling facility. So you had to tie up that memory anyway. And obviously a load more additional links, which again is documented in 74 subtype 4 with all the enhancements I will talk about in a minute. So as I say, for system-managed duplexing structures, both requests must complete. And response time is that of the slowest. Well, that's the good news, or the not so awful news, I suppose, because what that says is if you have a remote coupling facility and a local one, your requests are all going to take the time at least of the remote, not of the local, not some average of the two. So all requests are essentially with remote response times. High likelihood of requests becoming asynchronous. Okay. Now, let me address a point that I don't think is in any of my slides. There are numbers for synchronous requests that stay synchronous. There are numbers for asynchronous requests. That's it. There is a number called converted. Most of the time, I see nothing to speak of in the converted number. However, and this is the key point, the heuristic that dynamically converts sync requests to async requests, all those requests that got converted end up in the async bucket with no story about how they got there, right? We don't know whether they were always going to be async or whether they became converted to async, right? That's a crucial point. When you're looking at it, you can't just say, we're getting no conversions because the converted number says 0, because that's not the right answer. Okay. And actually, I play with the synchronous request percentage a little bit. As we see, it varies from with load. I think I might even have an example of this. Okay. So for low contention rates, applications might well have longer lock acquisition times, just because the time for the request, which says, yep, you can have it, takes longer. Okay. For user-managed structures, as I say, both requests to the two copies must complete, but only for the writes. So the writes are performed with remote because they happen to have to happen in both places, right? It's not like, and this is the key difference performance-wise, with system-managed duplexing, all the requests are essentially remote. With user-managed duplexing requests, by the way, think group buffer pools and nothing else, only the writes are. So if you have, let's say, a ratio of 10 to 1 reads to writes, that's a barely noticeable penalty. If you have this case, then it's a very noticeable penalty, okay? And may well drive requests to get converted to async. Okay. And just to cut this a little bit short, there are response time elongation measures in RMF, the peer weight and peer completion numbers, which document quite a lot of this. If you're getting big numbers in these, you have to think about it a little bit. Okay, so here is an example. This is at what I would call the 8-hour shift level. So we have a lock 1 structure here, and these are the request rates averaged across, I think this probably was prime shift. Yes, prime shift back in 2010, by the way. So don't take the numbers too seriously, but do take the dynamics seriously. So the blue numbers here are synchronous requests, right? And the red numbers here are async requests, including, just to ram it home, those that got converted by the dynamic heuristic. The changed here, there's a tiny, tiny, tiny veneer of purple. So what we have actually here is, for the copy in prod CF00, we have two systems, P0R0 and P0R1. And for the copy in prod CF01, we again have P0R0 and P0R1. And all I'm showing you here is the vast majority of the requests got converted to async. Because this is a lock 1. And the natural simplex, as we saw before actually, behavior is to be very short response time, be synchronous. Okay. Now, if we look at same shift, same thing. By the way, I see peer links here and InfiniBand links here. The request response times, this is why we're getting conversion. We are not, in fact, actually, but notice here, the lower response times here have more, if I come back here, have more sync requests, right? So there's less conversion going on. You can tell that from the data. Whereas the higher ones here, which are over InfiniBand links, we've got next to no sync left at all. Okay, so these numbers of response time, their prime shift average, which is very high level, I guess, kind of explain, in fact, very nicely explain the outcome in terms of sync versus async requests as actually executed. Okay, and by the way, let's try this with load. So in this particular case, I think we have a certain amount of unpleasantness here because I would say, this is the response time here, the response time is taking off as the load builds up. Not a wonderful situation to be in. So we're possibly okay down around the 1,000 to 4,000 requests a second, but we take off when we go above 4,000 requests a second. You know? So that's an interesting dynamic. And by the way, the sync percent here stays fairly rottenly low, and I think it goes actually lower as the request rate builds up.
You've got two strategies there. I presume you could change your sync to sync setting to make everything sync and be damned, async and be damned, so you release the CPU quicker, or shift it the other way to wait longer on sync.
Right, and obviously bear in mind what you just implied by increasing the threshold, right, which is more requests going sync, which means more coupled engine CPU, meaning the ZOS, because it's going to spin waiting for the sync request to complete. So, yeah, it depends what you're optimizing for, very much so. And most people don't fiddle with the settings, to be honest. If you want to fiddle with the settings, you better know what you're doing and better be prepared to measure and perhaps go back to the settings or change again. So that was all the normal today way. The futuristic way of tomorrow is asynchronous coupling facility duplexing. So here, the point is to make duplexing of lock structures more practical even at extended distances. The requests now, instead of going to both places, go to the primary. And the secondary structure requests, the updates caused by those requests, happen asynchronously with respect to the primary updates. So that takes out a lot of the coupling facility to coupling facility latencies we see today. Now, the way it works is the secondary requests are sequenced, so they still happen in the right order in the secondary requests. Now, the key thing I think that's important here is, and this is only going to apply in DB2 terms, I think this is only DB2 by the way, DB2 12 at that, that's another slide gone. At DB2 commit, all of that queue of requests must complete. So you're going to be waiting if they haven't completed anyway, right? Meaning in both coupling facilities. So this is slightly speculative, but bear with me a second. The effectiveness is going to depend on the nature of the DB2 work. Right? Because if you're very, very frequently committing, maybe the asynchronous thing doesn't work quite so well for you, if you think about it. Whereas if you infrequently commit, which you might or might not want to do, then the impact of at commit time, that's going to be lower. That's what I would think, not having seen data for this. It's a way of thinking about it. Just bear in mind, at commit time, all those secondary writes have to have happened, or they happen as part of it, effectively. The other thing to bear in mind is primary structure distance effects are not avoided by this because we've done nothing to the primary. We've only done something to the way the secondary update happens. So distance is still going to matter in this case. Okay, so this is basically, to repeat a little bit, so if this is DB2 via IRLM, Lock Manager, so we get a request into XCS component in ZOS, and that will actually send the request to the primary and get a response back fairly sharpish. And then XCS will give that response back to RLM and DB2. Meanwhile, there will be communication that gets the ordered queue, and communication between these two as well, that gets the ordered queue of requests that need to complete. And that will get executed in the right order. And that's a key thing, that it's in the right order. And that's very different from the way duplexing works today. So you need to be on a reasonably modern processor with CF level 21 and a service level on top of that, or at a specific service level. ZOS 2.2, you can do it if you're running ZOS under VM, but VM has to be at the right level as well. DB2 version 12, and I would imagine IRLM 2.3 is probably a correct for that, at the right APAR level. So there's a certain amount of getting there, particularly probably the DB2 version 12 thing, because that tends to be quite a slow train coming. So those are the prereqs for that. In RMF, to keep this fairly brief, we have support in the post processor and we have support in the 74 subtype 4 record. And we have coupling facility level details, and we have coupling facility to coupling facility. In other words, remote coupling facility data that's been reworked, that section to add extra stuff about channel paths and timings. And then in the 74 subtype 4 data itself, we also have structure level information somewhere in the middle of this slide. So RMF has got support for that. I'd love to see data, by the way, as you would imagine. So I'm going to change tack completely and talk about XCF for a moment. So people don't tend to tune XCF, despite what Don's good work says we should do, right? And actually this piece is not about that. I'm interested actually in what I call nosiness, which you might, if you want to use a posh term, called architecture or infrastructure. And what does this state look like, and what does it look like to be customer XYZ? So traffic analysis, I think, is kind of interesting. So the first thing to say, by the way, is XCF traffic is divided into groups. Most of the time, the XCF group's member name in it is useless, but we have a new field, well, about 10 years old, so I guess that's new, which is the job name, the conversation between me and RMF was, could I have job name as well as member name? And the answer is, well, actually, it happens to be the very neighbouring field in the record we get back from XCF, or the field, the data area we get back from XCF. So job name is kind of useful, as we will see. So traffic analysis, in other words, request analysis from where and to where, explains a lot about the performance. And in particular, one of the things that's worth thinking about is, if you have a lock1 structure for DB2 data sharing, there are two XCF groups that are associated with it. One to do with XCS and one to do with RLM. And understanding their traffic and understanding how to tune those and maybe getting their traffic down is quite a useful thing to do. More interesting perhaps, and you'll see this on the next slide I think, is topology. You can see a certain amount of topology without special instrumentation, namely DB2 instrumentation, for example. So the two examples I would give, as I say, is the DB2 one, which we'll see in a moment. The other one, though, is kicks. So kicks to kicks XCF traffic normally goes through a group called DFH-IR000. Now, since I wrote this slide, I think one customer said we have multiple kicks XCF groups, but it's very, very rare. And you can play guessing games of this kicks region. Does it talk to this kicks region? By the way, health warning on that. Not all the kicks to kicks traffic that you would see is done through XCF. So that's a bit of a blunt instrument. But here's a happier story. So this is a real customer. I'm desperately trying to remember who it is. They have 20 DB2 subsystems in 8 data sharing groups. Now, I happen to know the subsystems actually from the RLM names, and these are things like DB03, DB1, blah, 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 because they will be called DB03 RLM, etc., right? And obviously I know the systems they sit on, again, from 74 subtype 2 XCF data. Now, the interesting bit to me is, what is the group? Well, the group, as I say, every data sharing group has a lock1, and every lock1 has 2 XCF groups. One of them has got a silly name like IXCLO something, right? Totally unmnemonic, totally useless to anything apart from let's get the traffic down. The other one, though, is normally called something like, and I would guess from this one, DXRB0, I guess that's a G, right? So if you've got the job name, which I mentioned just now, and you've got the group name, you've got the data sharing group structure. You know these address spaces, these RLMs, are in this data sharing group. Now, probably I hacked the DXR off the front of the group name in my code, because nobody calls a data sharing group DXR something. They call it something and put DXR on the front when they set up the XCF group. Similarly, these are probably IRLMs rather than DBM1s, masters, blah, blah, blah. But the point is, this is a real example where this code basically took the 74 subtype 2s, did some fancy stuff, and out pop, I think, 7 non-production data sharing groups. It turns out, by the way, I manually color-coded this. You can't tell from 74 subtype 2 what's production and what's not. You can kind of guess, because high traffic, low traffic, right? But that's not really definitive. But this stuff came out of 74 subtype 2. So I'm a big fan of not having to go to DB2 instrumentation until you really must, because my record for the number of DB2 subsystems in the customer that I've seen so far is 135, which is a hell of a lot of DB2s, right? You're really going to collect accounting trace, statistics trace from all of those? I really don't think so. By the way, that's 35 data sharing groups. Yeah, I mean, it's the way it goes. And it's not an SAP one, which I'm working with an SAP customer right now, and that would make sense for them, but it's not. So being able to pull out topology without specialist middleware instrumentation, I think, is really very handy. So this is one of the reasons why I get quite excited by 74 subtype 2s. Oh, by the way I did this was I create a CSV file from the 74 subtype 2 in my recs and pump it into a nice Mac-based mind mapping piece of software, would you believe, called iThoughts. You could do it with Mind, though. You can do it what the hell you like, so long as it actually can depict trees and you can feed the beast, right? But basically, this is one of the tricks we play. And if I'm saying to you, I see your production data sharing group with these members on these systems and a lot of traffic going to it, I'm several steps ahead of where I'd be if I had to ask you what your DB2 topology was. Now, you can play the same stunt. You don't have to graph it necessarily, diagram it, but keeping track of what's going on your machines, I think, is quite important. So that's a nice example. Okay, so speed up a little bit. Cupping facility path information. This is a fun one. So in CF level 18, which is quite old now, but this is one of these ones where you go, is it worthwhile banging on about this because it's 2 machines old? The answer is hell yeah, because people still aren't doing this and there's value in it. So there's an RMF APAR, quite old now, which updates the 74 subtype 4 record and the coupling facility activity report. So what it gives you is configuration information for the links. And it's detailed adapter and link type, physical channel ID, chipid. And oh, by the way, even if you're not CF level 18, you get some of this stuff. You get chipid. Well, big deal, but you do. Okay, and I have to say this is InfiniBand, ISC and ICA, SR, and actually the long reach ones now only. One key thing here, which almost makes it vital, it probably does make it vital that you actually do something with this, even if it's only look at the report every once in a while, is this degraded flag. It's a bit flag. If you see it set, if you see it in the report, and you will if it's set, call your customer engineer, because when I talked to the hardware guys in Poughkeepsie about this stuff, because I wanted more, I always want more out of the instrumentation, they said, that's serious. If you get that bit set, you call your customer engineer. There's another set of circumstances under which you do, which I'll come to in a minute. Okay. The other interesting bit, which is where the fun lies, to me, channel path latency time. Okay. So what that is the time taken for a round trip of a signal from one end of the link to the other, right? And you can measure it with a thing I'm told is called a reflectometer. 10 microseconds of turnaround time is 1 kilometer of distance of the link, right? So that gives you a distance estimate. And in fact, I think that's exactly what's reported in the RMF post-processor report. It would be interesting, by the way, if that ever degraded, because that would mean, you know, dirty contacts, blah, blah, blah. I've not seen that happen. In normal running, it wouldn't. Okay, let me skip that and that. So I started off with a blog post that basically talks about that data. Right? And just to take the story swiftly through the various blog posts, the first thing that happened was I got the data from a customer in the Netherlands. And I thought this was quite interesting. They had 3 routings between their 2 data centers, and they were something like 8, 12, and 15 kilometers. And I can't remember how many links it was in each routing, but the numbers were clearly different for the latency, right? What was interesting was I presented the numbers I saw from the latency data. It was different from what the telco had told them. You know, and it wasn't a case of we consistently overestimate with the data, because some were higher. I think the middle ones were bang on, and the lower ones I think were probably a bit high or something like that. There was nothing that said we're systematically worse or better, higher or lower. So I thought that was kind of interesting, because if that happens to you, if somebody says, well, your link's 1 kilometre and it's 25, you know, you wonder what the hell's going on, and you actually probably should investigate. I'm told there's a thing called a fibre suitcase or something like that that people accidentally leave in sometimes when they're testing what happens over distance. So verify, I guess, is the answer to that one. And then when I presented this in Paris a couple of years ago, I think I must have followed Mana around by about 1 day or something, not quite sure, it was probably one of those. A customer said, so we looked at this latency data because we spotted it, and it said the wrong numbers on one of the cards and not the other card, or something like that. And they said, so we had an argument with the customer engineer, because the customer engineer was adamant, oh, it's only instrumentation. And they insisted and escalated, and they got the card changed. And my point of view on that is, if the instrumentation is wrong, I think I would want that card changed too. I just can't see why you wouldn't, given if that's going wrong, what else is going wrong, you know? It was something like they knew it was 5 kilometers, and one card said it was 8. And their routings across all the other cards were spot on 5, or whatever it was they were supposed to be. So, yeah, I've had a lot of fun with this one, but the basic point is verify, and it will actually give you some view, I suppose, of the actual effective distance if you start pulling things apart. So it's a very rich piece of instrumentation. So I think that's rather nice. Very briefly, coming back to thin interrupts, by the way, there's a very nice paper by Barbara Weiler on coupling facility thin interrupts. There is a new flag bit. So if you want to verify, again, that V word, that it's actually turned on, then this bit is set if dyndisk equals thin is enabled.
There's a very, very nasty Z13 hyper on thin interrupts at the moment.
Is there?
Warn people. Yeah.
Right. And as I say, I mean, I think thin interrupts is a minority sport in any case, most of the time. One other thing, though, is you get lots of shared coupling facility LPARs, which are, if you like, in a test category, and nobody bothers to instrument them with 74 subtype 4. In that case, you should expect the difference between physical dispatch time and effective dispatch time for the coupling facility engines for those shared CF LPARs to be greater than they were before, because Prism is actually having to do more work there. So that's a minor footnote on those.
Mark?
Sure. Do you want to come back?
That last point, just to turn that into English, is that your dispatch thin CFs will be 80% busy, but they're not getting their...
No, that's a different point. Actually, that's the P-way time going down.
Right.
Because the busy is P busy over P busy plus P-way. That's a different phenomenon. That's also true.
It's not waiting for work anymore. It's giving up the engine.
Sooner, yes, which is a better behavior.
Yeah. But what you need to be concerned with is what percent of its share is it taking, not what percent busy is it, because you can see it's taking 0.0002 engines, right, and your share that you gave it was a quarter, so it's not doing anything. Right. And this point is a bit of a different one. It's basically, if you don't have the 74 subtype 4 for a shared coupling facility LPAR, the one thing you might well see is a bigger PDT minus EDT than you expect, because there's more work being done by Prism to manage in the thin interrupt case. So that's a minor footnote.
Yeah, so it does weird things to the data model as part of the reason for putting thin interrupt stuff in here. So, Z14, miscellaneous, well, we have a new long reach link. I'm not going to talk about structure encryption, apart from say two things. One is the structure encryption is actually not done in the coupling facility. It's done in the coupled ZOS, right? So don't expect the coupling facility CPU to go up, but if there is a CPU cost, it will be in the ZOS, right? That's one thing to bear in mind. The other thing is, at the structure level, 74 subtype 4 actually documents whether the structure is actively encrypted. Okay. The next thing is, and I think this is more to do with larger numbers of engines in the coupling facility image than smaller ones, CF level 22 changed the way the dispatcher works, essentially to be more efficient by dividing the work up into different kinds of work queues in a better way. Okay. That's what this all said. And the other point is for list structures, notification enhancements, a lot of that has been rewritten on behalf of exploiters. One of them is XCF and the other one is MQ. Okay. So that's a nice little set of notification enhancements. Okay, so let's wrap up. Hopefully I've shown you that we've come a long way with coupling facility CPU instrumentation over the last few years. So capacity planning, just to repeat, is now down to the structure level, which I think is a very good place for it to be. But note, the thing I might have ought to have said sometime earlier in this presentation, the 74 view of coupling facility structure CPU is for everybody sharing that structure. Right? You don't get a different set of numbers from each system. So you can't say sys A basically uses a quarter of an engine's worth in this structure and sys B uses half an engine's worth. You can't say that. The only way you could even get close to that is by proratering, which is not scientific. So there's one number per structure in an interval for the coupling facility CPU. Fair enough, but it's a big advance. The next thing is if you are into shared coupling facilities, we can now tie up the partition data report view and the coupling facility activity view. Next thing is, I've shown you some things that you might already be doing and some that you almost certainly aren't. It's always time to keep revisiting your reporting. It's particularly so of parallel sysplex. A lot there to think about. Structured duplexing needs particular care, even, I would say, in the async CF duplexing case. You really, when you introduce that, need to be measuring what you're doing. Not because I think it has risk, but simply because you need to understand whether it's brilliant or just wonderful, yeah, or so-so. XCF traffic, there's a lot I could say about why that's a fun game to study it. The coupling facility link information is a useful emergent topic, is the other thing I would say, for all sorts of reasons, including verification. So, that's it. As I said, I've gone all over the place with lots of different aspects of parallel sysplex performance and the instrumentation, and hopefully it's given you a few ideas to do stuff with.
And a lot of people don't realise that the number of structures you have relates to how many threads you've got across SCS, how many concurrent operations you can have,
right.
Data.
Right.
A lot of people don't spot that simple.
Right. No, I think you're going to like doing stuff at the engine level. Yeah, and that's that line of thinking is one of the reasons why I put in the 744 P-way and P-busy numbers being at the engine level. Good point. Okay, anything else?
We've come up to time. I'd like to thank Mark for putting a lot into this hour. We did start a few minutes late, and there's a 30-minute break now, so I think we have time for a question or two if anybody has one.
You mentioned about a 50% rule of thumb.
Yeah.
About, well, if this is for your second failure, your second CF failure.
One of the reasons is for second CF failure to decamp the vital structures into it, but also actually, I think it's fair to say that you wouldn't want to drive much harder than that ordinarily anyway because of the queuing regime. It's a bit like zips, you don't drive them too hard, right?
I was going to say, if everything is duplex, you've got the CPU hit already, so you haven't got.
Yes, that's right. This is why I talk about white space may already have been eaten. Yeah, both for memory and for cycles. And at least with the structure level data, you know how that game plays in much more detail than if you just go, this one's this busy, that one's that busy, and at the coupling facility level. Yeah. Okay.
More questions?
I'm curious about the CL5 speed.
So am I.
The red book is rather vague.
And so am I, because I have nothing to say to you on it that hasn't already been said, I'm afraid.
We have one, but I don't know if it's any faster yet. So.
Right, and I don't know that anybody said it should be.
No, they didn't say it should be. No, I realize that.
Right.
But I'm kind of, you know,
Yes. I'm told it's good. I'm told it's good for hardware planners. I'm told it's a good thing for hardware planners, which might be being unfair to weakly say that, but that's what the gist of it is. I don't think it's designed to be a performance step up from what it replaces, you know, InfiniBand.
Yeah, the distance latency issue is still there. It's using the same fiber. Yeah.
Same speed of light, same 10 microseconds round trip per kilometre. That isn't going to disappear, I don't think. Okay, anything else?
Okay.
Alrighty, thank you very much for your
No
time.
more questions? I'd like to say thanks to Martin.
Thank you very much.